Welcome to another deep dive. Today we're going to be talking about making hydrogen fuel, but get this, we're going to be using methane to do it.
Oh yeah, that's a good one.
Yeah, so it's that gas we're always trying to reduce because of its impact on the climate. But turn it out, we might be able to use it to our advantage.
Yeah, that's the idea, turning something we think of as a pollutant into a clean energy source. That's the whole potential of methane pyrolysis, right?
Okay, so to get into this, we're going to be looking at a research paper from way back in 2008. And it gets pretty technical, but we're going to break it down, don't worry.
Absolutely.
So basically, they took methane and they zapped it with heat to break it apart.
Right. And the paper gives us this really simple formula. So you have CH4, methane, and that breaks down into C, which is solid carbon, and 2H2, which is hydrogen gas.
Okay, so 2 hydrogen molecules for every methane molecule. That's pretty good.
It is.
But I'm guessing it's not that straightforward, right?
Well, there are some challenges. First of all, this reaction, it needs some energy to get going, like a good kick in the pants, right? And then the catalysts, you can think of them as little helpers that speed up the process. Well, they can actually get gummed up by the carbon that's produced.
Oh, okay, so it's not just breaking things apart. It's about doing it efficiently and not creating, new problems, right?
Exactly.
Okay.
That's where the researchers in this study got really creative. They used something called activated carbon.
Okay, now I know carbon is one of the byproducts we're trying to manage here. So why use more carbon?
Well, that's what's really cool about activated carbon. So you can make it from stuff like coconut shells. And it has a really high surface area, like picture a teaspoon, right? That has the surface area of a tennis court.
Wait, a teaspoon? Seriously?
Yeah.
Wow. Okay, so that huge surface area must be important for making the process work, right?
It is. It basically gives the methane molecules a lot of places to interact with the catalyst and break down. But here's what's even cooler. Activated carbon is also really good at absorbing microwaves.
Did you say microwaves?
Microwaves, yeah.
So they're zapping methane with microwaves to make hydrogen.
That's right.
I kind of love that. But why microwaves specifically?
Well, microwaves are known to actually speed up certain chemical reactions. So in this study, they compared using a standard electric furnace to using microwaves. And the results with microwaves were pretty wild. So they added nitrogen gas to the mix, and it supercharged the whole process.
Wait, hold on. Adding nitrogen, wouldn't you want to keep the methane as pure as possible to get the most hydrogen out of it?
You would think, right? But here's the thing about nitrogen and why it's actually so helpful, especially with microwaves. First, it seems to distribute the methane more evenly within the activated carbon. So you're making sure that more of it comes into contact with the catalyst. Think of it like baking a cake, right?
Okay.
You want to mix all the ingredients really well.
Yeah.
Kind of a similar concept.
Okay, that makes sense. But that's just one reason, right? There was another benefit to the nitrogen.
Yes, and this one's even cooler. They believe the nitrogen, when it interacts with the microwaves, it creates these things called microplasmas.
Microplasmas?
Yeah, so they're imagine these tiny, super hot zones that form inside the reaction chamber.
Wow.
It's like having these little bursts of energy that just boost that breakdown of methane.
So it's almost like they're adding fireworks to the mix? Is that what you're saying?
Yeah, yeah.
No wonder the conversion rate's shot up. Okay, but why wouldn't this happen with a regular electric furnace, right? Wouldn't those hot spots just form regardless of how you're heating things up?
That's a great question. And it seems like those microwaves and the nitrogen, they work together in a really unique way to create these more intense microplasmas. It's almost like the microwaves are, choreographing this dance of the energy in the molecules.
This is making me realize how much we actually just don't know about how things work at such a small scale,
Oh, absolutely.
It's really interesting. Okay, so you mentioned earlier that there was a second surprising finding from the study, right?
I did.
So what else did they discover?
Well, with this whole microwave and nitrogen thing, they found that carbon nanofibers started forming on the surface of the activated carbon.
Nanofibers. Wait, are we talking about those super strong, tiny materials they use and all that, cutting edge tech?
Exactly.
Really?
Yeah, it seems that with those microwaves and the nitrogen and the activated carbon all kind of mixing it up, the carbon atoms were like, hey, let's be organized. They started forming those superstructured fibers instead of just being, a shapeless blob.
Hold on, so we're starting with methane gas, right? We zap it with microwaves, toss in some nitrogen, and we end up with hydrogen fuel and carbon nanofibers. That's pretty awesome.
It really is, and the images from the scanning electron microscope, they show these nanofibers, and they're crystal clear.
Well,
You can actually see them in the paper, figures 5C and 5D, if you're curious.
I'll have to check that out.
Yeah, it's worth a look.
Okay, so this is really incredible. It's like turning trash into treasure, but on a, molecular level.
I like that.
But do the researchers know why these nanofibers form? What's the nitrogen doing in all of this?
Well, that's the million-dollar question, and to be honest, the paper doesn't give us a clear answer. They basically say, hey, this nitrogen thing, it's complex and we need to do more research.
Oh, okay, so like a scientific cliffhanger.
Exactly. And those are always exciting.
Yeah, yeah, definitely keeps you on the edge of your seat.
Right.
Okay, so before we go too far down the nanofiber rabbit hole, I think we need to recap what we've learned about this whole methane pyrolysis thing because we've covered a lot.
Absolutely. So the main thing to remember is this. Combining microwave heating with nitrogen. That seems to be a really promising way to get hydrogen gas from methane. It's way more efficient than just using a plain old electric furnace. And then bonus, you get those potentially valuable carbon nanofibers.
Right, right. This one study's opening up all sorts of amazing possibilities, but I think it's important to remember.
It's just one piece of the puzzle.
Right.
More research is needed to see if we can scale this process up, take it from the lab to the real world. But it does give us a glimpse of this future where we could actually turn harmful waste gases into, well, valuable resources.
Yeah, I'm starting to picture a world where we're not just capturing methane emissions, but actually using them. We're creating clean energy and all these incredible materials.
It's a vision worth pursuing. And it kind of brings us some important questions.
Okay, before we get into those bigger questions, though, I want to go back to something you said about the activated carbon.
Uh-huh.
You said that it eventually gets deactivated by the carbon buildup. So what happens then?
That's a great point. Even with this setup, you can't avoid having some carbon byproduct. But that's one of the perks of using a carbon-based catalyst. Unlike metal catalysts, which are kind of a pain to regenerate, you can actually reactivate activated carbon. It's pretty straightforward. You just burn off some of that extra carbon.
Oh, so it's like hitting the reset button.
Exactly.
Okay.
Easy peasy.
But wait, wouldn't burning carbon release CO2? And that kind of defeats the whole clean energy thing, right?
That's a good point. And researchers are definitely aware of that. There are ways to capture and reuse that CO2. You can use it for things like industrial processes, or you can even store it underground. That's called carbon sequestration.
Right, right.
So there are options.
Okay, that makes sense. So we've got this cycle, right? Methane turns into hydrogen and carbon. We can use that carbon, maybe even make those nanofibers, or we can reactivate it, and then hopefully we're capturing that CO2 that gets released during reactivation.
Yeah, it's a bit of a balancing act.
Yeah, a lot to keep track of.
It really highlights how, well, everything's connected. You can't just look at one part of a new technology, especially if we want to make it truly sustainable. You got to think about the whole shebang,
I see what you mean.
the whole enchilada.
Thinking about all these different factors, it reminds me of something else the paper mentioned, volumetric hourly space velocity.
Oh yeah, VHSV. It's a mouthful.
Yeah, what exactly is that, and why is it important?
So VHSV, it basically tells you how quickly the methane gas is flowing through the reactor compared to the amount of catalyst that's hanging out in there.
Okay.
A higher VHSV, it means things are moving fast.
So faster is always better in this case.
Not necessarily. It's a trade-off, really. Faster flow means you can process more methane, but the methane molecules have less time to, hang out with the catalyst and do their thing. So you might end up with less conversion.
Okay.
Imagine trying to cram a whole bunch of people onto a bus.
Uh-huh.
Some folks might get left behind.
I like that.
Right.
So they were trying to find that sweet spot between speed and efficiency.
Exactly. And it just goes to show it's not just about the chemistry, it's about the engineering, the fine-tuning of the process, especially when we start thinking about scaling things up.
That makes sense. So speaking of scaling things up, if we could make this work on a large scale, how could it change things, like the whole energy landscape?
Well, for starters, it could give us a cleaner way to produce hydrogen. And hydrogen is already seen as a key player in moving away from fossil fuels.
Right.
You can use it in fuel cells for electricity. You can power vehicles with it, heat homes, all without those nasty emissions.
So it's like a clean alternative.
Exactly. But it all comes down to how you make that hydrogen.
Right, right.
If you can make it from methane without all that greenhouse gas baggage, that's a game changer.
Totally. And this technology, it's not limited to methane, right? The paper mentioned using it on other waste gases too.
Oh, yeah, absolutely. Methane is just one example. There are tons of gases out there that have carbon and hydrogen, and this method could break them down. We could be making all sorts of sustainable products from things we currently just toss out.
Wow, that's incredible.
It really is. It's like imagine industrial facilities become these like alchemists, turning their emissions into valuable resources.
I love that. It's a really inspiring vision for the future.
It is. And this research shows that vision might not be so far-fetched.
This whole conversation has been so eye-opening. I'm starting to see methane not as just a problem, but as an opportunity.
That's what's so cool about science. It helps us challenge those assumptions and see potential where we didn't even know it existed.
Okay, so before we get too carried away with all these possibilities, we have to remember this is still early stage research.
Right.
There are challenges to overcome before we see methane pyrolysis taking over the world.
Oh, for sure. Scaling up any process like this always comes with its own set of hurdles, from figuring out the engineering and the costs to making sure it's safe and doesn't harm the environment.
Yeah, we can't get ahead of ourselves, and even though this research is super promising, it's just one study, we need more research to really know if this approach is going to work long term.
Absolutely. But that's how science works. It's all about discovery and then refining those discoveries and then innovating.
Right, who knows what other surprises are out there. Maybe we'll find even more uses for those carbon nanofibers or discover catalysts that are way more efficient. The possibilities seem endless.
They do, don't they? That's what makes this field so exciting.
Okay, so I think we've given everyone a lot to think about today. We went from the nitty-gritty chemistry of methane pyrolysis to its potential to change the world. It's been a wild ride.
It has. I hope you've all gained a new appreciation for the power of turning waste into something valuable.
But before we wrap things up, we want to leave you with one final thought, a question to ponder as you go about your day. So we've been really focused on methane as our starting point for making hydrogen.
Yeah.
But what if we could use this same concept, this whole process, on other waste products? Could we use this to transform other things that are, pollutants into useful stuff?
That's a fantastic question. We always talk about cleaning up the environment,
Right.
reducing emissions, which is super important.
Uh-huh.
But imagine if we could go even further, actually using those emissions, those waste products, to make something new.
Yeah. So instead of just cleaning up the mess, we're actually using the mess
Right?
to make something good.
Exactly. It's a whole different way of looking at things.
Yeah, it is. Okay, so imagine carbon dioxide,
Uh-huh.
which now contributes to climate change. What if we could capture it and use it to create, new materials or fuels or even food?
It sounds crazy, right?
Yeah.
But, like we've seen today, sometimes those crazy ideas, they turn into reality.
Yeah.
The key is to stay curious,
Yay.
keep asking questions, and never stop wondering, what if?
That's great advice. So if you're feeling curious after this deep dive and you want to learn more, check out the show notes for a link to the original research paper.
Oh, yeah, definitely check it out.
You can, delve into all the details. Maybe you'll even find something the researchers missed, challenge their findings. Who knows? Maybe you'll be the one to make the next big breakthrough in sustainable technology.
You never know.
All right. So until next time, keep diving deep, keep those brains engaged.
Yeah, absolutely.
And remember, the future is what we make it. See you in the next deep dive.